Okay, picking up where we left off, we're on page 285. We just finished talking about how router aggregation. There's a cool little thing in the book. I don't have the graphic up here where they have, 5 networks and they all talk over the same link every single time. So why not just combine them together into one? It's kind of simple. So people sat around and looked at that and went, that's pretty damn smart. Why don't we just continue that kind of thinking? For example, why don't we just automatically configure a west-east coast route through Time Warner? Because almost all the traffic that's entering in from California going to New York is most likely going to go through the exact same set of routers. So why not just have, like the interstate system, why not have major arteries going east-west and north-south? Wouldn't that kind of make sense? And because without that kind of thinking, all right, remember I talked about the only way to get from Killeen to Lampasas is to go to Copper's Cove and ask them, right? Well, why not have an entire path point out saying, here's how you go from California to New York and skip all the intermediate things in between. Okay, you could reduce down the number of hops. Well, let me rephrase that. You could reduce down the number of routing decisions a great deal. Now, one more time, let's talk about how things work now. All right, things work now is every single packet is examined and determined where the route is. Okay, let's say I sent 10 packets. It's going to look at that first one and go, well, let's see how we're going to send that. Oh, we're going to send it over here. Then it's going to look at the second packet and go, wait, I guess we need to figure out where this goes. Let's send it over to port number 42. And then the third one, wait, let's figure out where it goes, and goes to 42. It does not remember you, okay? Every packet has to be examined and routed, and a routing decision make, even though the same destination may have been on every single packet. It does not say, oh, I've already figured this out. It looks at every single one of them and routes every single time. Okay, so that's kind of messy, isn't it? So these interstate systems, because these are autonomous systems, they don't really work between autonomous systems, okay? But I could put an interstate inside an autonomous system. So inside Time Warner, I could have an interstate system that cuts east-west. And inside Sprint, I could have another one that cuts east-west. And inside Comcast, I have another one that... And so I could reduce the amount of routing decisions by saying, take route number 4. And then I would go to the next autonomous system, and if it was playing the same game, it could say, well, you need to take route number 44. And so it would reduce the amount of routing decisions. And further, once you've picked one of these routes, it's pretty much for certain that all future packets going through that are going to go through that exact same route. That's not the case under normal scenarios. Normal scenario is I send a packet and maybe one of them takes this northern route and maybe the very next packet takes a southern route to get from east coast to west coast. You don't ever really know. You're not in control of how those autonomous systems work, so you don't know. So they created a thing called the multi-protocol label switching, MPLS, page 285, that talks about doing what I just said. Instead of having the routers inside these autonomous systems try to figure out how to traverse an AS, they just have some pre-built typical paths, right? Up the interstate system. They go, look, we have an awful lot of cars that are going to go enter our autonomous system over here and leave our autonomous system over here. So why don't we just build like a permanent route, an east-west permanent route? And so I'll just put a label, MPLS, the label part. I'll put a label on there that tells it what preferred route to take. Okay, so MPLS, the routing before MPLS, let me start over. The routing information was stored inside the IP header, and you had to read the IP header. You had to get the source and the destination and the number of hops and all the rest of that stuff. You had to get that. Then the routing decision was made for each header. Nothing was learned from the previous one. It wasn't like, oh, well, I've already figured this out once. And then the last one is the path that was chosen could change over time. With MPLS, they use a label that basically has the destination route. The label says use route number 42. That's it. That's all. So it doesn't have to look inside the IP header and figure all this stuff out, because there's no routing decisions whatsoever. I'm telling it, take the interstate. That's it. No routing decisions to make. So these things are potentially faster. They're better for the autonomous systems because it speeds things up, and they don't have to have highfalutin routers with all this processing capability, because there's no routing decisions being made. Okay. So it sends a packet like through a predefined route, an east-west route as an example. This is done at the beginning when you set this thing up, right? So at the beginning of transmitting this packet, I say, well, I'm going to use route number 4. And so I don't have to make a decision after that. Well, except when I get to an edge of another autonomous system, because, my route number 44 might turn into your route number 12. Okay. And MPLS, because it's it's I'm not sure, it's interstate based, using the traffic analogy. All packets almost always follow the exact same path, which is good for reliability, good for latency. It's all or nothing kind of a thing. Once I commit to a route, it's going to be consistent. Kind of cool. Now, you could use MPLS in even a smaller environment to produce essentially like a private route. So let's say, for example, that I'm in an area that's served by Sprint, and I have 2 buildings and they're 5 miles apart, and I want to connect them together. I would go to Sprint and say, hey, I need 10 up, 10 down path between these 2 buildings. Are they going to say, great, we're going to go run you some fiber and it's going to cost you $500,000? Is that what they're going to do? No, because both areas are already being served by Sprint. What they're going to say is, we'll hook you up an MPLS circuit between, and because it's now the purpose for putting a label on there isn't to bypass all the routing decisions and all the rest of that crap. This is a special case where I'm segregating my traffic so only the people who have a label on it get sent through this wire. And if you have a label on it, you get sent back through the wire, and no other traffic goes over that communication channel. Now, I said channel, not wire. I mean, clearly the cable is going to be carrying lots and lots of traffic, but that particular communications channel could be dedicated to you, and they could allocate processor power, RAM, CPU speed, those kind of things, to give you the type of latency or throughput or whatever it is you want. So MPLS could be used in a small environment. Now, could I go to Sprint and say, okay, I want to connect to this other building on Comcast using an MPLS circuit? They would go, yeah, but it's going to be different, because in that context, MPLS is inside their autonomous system. They could make an MPLS that connected to yet another MPLS, but then there's more people involved, right? I have to go talk to 2 different people rather than one. So if you have one internet service provider that connects all of your buildings together, for example, if they're a couple miles apart, MPLS is actually pretty cool. Okay, so it is somewhat analogous to like virtual private network, where I tunnel through the internet and I have my own private LAN that's just mine, although in reality the cable that's running this is going through all sorts of places. Now, does the MPLS have encryption just like a VPN? Nah, not really. I mean, you could add in your own encryption, but what I'm just saying, MPLS by itself is just a switching technology. That's all it is. It's just how to simplify the switching decisions. Plus, this really cool technique we just talked about on how to segregate traffic in a multiplexed cable. Okay. The other thing that MPLS can do, it can handle practically any type of layer 2. I mean, if you got a leased line or a frame relay or a asynchronous, ATM or Ethernet or fiber or whatever, it doesn't matter. It's kind of sort of like IP. In fact, some people say that MP is IP on steroids. Okay? It's like an enhancement to IP, an alternative to IP that routes packets better than IP. And they are absolutely correct. IP was designed to be incredibly generic and work for everything, and therefore it's got some really rough edges when it comes to how to get from point A to point B through this gargantuan clouds of autonomous systems. This is a pretty cool technique for getting stuff through interiorly, through an autonomous system, but not necessarily from one autonomous system to another. Okay. So the what happens is I have some data, and I have to make sure my router is a label switching router. Okay, that's one thing. And so I get an MPLS header that's actually stuck in here. And so when the router gets this, by the way, this is the example of entering or exiting an MPLS. So if it's going this way, this is data inside my network that wants to wants to jump onto the MPLS. All I do is just add an extra label on here. So the router doesn't have to read the IP header. It doesn't have to read the MAC header. All it has to read is that one tiny label. And the label is going to say, use route 42. That's it. And so this guy says, got it. I know what pre-programmed route number 42 is. And by the way, we're never going to discuss how you set up these default routes. Okay, that's some other class. So coming back this way, it's going to just get here and it's just going to strip that MPLS header off, and then presto changeo, I'm talking again. So it's actually pretty doggone cool. All right. We're almost done. On page 288, they talk about along the same lines of MPLS, everyone agrees that the use of autonomous systems and these edge routers and all this stuff is clumsy. And somebody needs to put their heads together and come up with a smarter way of analyzing this. So they have the thing out there called OpenFlow, and it's basically a software suite that you use to analyze the traffic going through your autonomous system and look at it and say, if you were to divert this type of traffic from this router to this router, it would speed things up. So it's like a router, a super duper high elevation style routing management system. It's like a super operating system that's controlling, if I'm Time Warner, controlling several thousand routers. So that's a cool way of instead of going to each individual router and tweaking stuff, right? You have this gargantuan overwatch of all of your routers. So that's what OpenFlow is all about. So since routing is complicated and each autonomous system is authorized to do their own thing, optimization may not be possible at all. Or the optimization that occurs really isn't optimal. It may be optimal to them, but it's not optimal to me. So centralized route management gives you the bigger picture, and the bigger the picture you make, the smarter the routing decisions you make. So instead of configuring each router to figure out how to do things, it would make sense to have a traffic cop look at all of the interstates and all of the roads and start making decisions for these routers. That's what this thing is all about. Okay, ladies and germs, we have reached the end of the chapter, and we'll see you guys again in some future chapter.